Hello, and welcome to Fun Facts Online, the podcast where we dig deep into the science that shapes our world. Take a look at the device you're probably listening to this on right now. Your smartphone. It's a sleek rectangle of glass and metal, a portal to the entire world in your pocket. But what if I told you that this little device is also a battleground for global superpowers, a key player in the fight against climate change, and the source of some of the planet's biggest environmental headaches? Because hidden inside your phone, and inside countless other technologies we rely on every single day, is a set of 17 chemical elements. They are the secret ingredients, the unsung heroes of our modern age. They are the rare earth elements, and their story is a fascinating, complex, and incredibly important tale of science, politics, and our collective future. So today, we're going on a journey to uncover the secrets of these miracle materials. We'll find out why their name is completely wrong, what superpowers they possess, how they've become tangled in a global tug-of-war, and what we can do about the heavy price our planet is paying for them. It's a story that's bigger than you think, and it affects all of us. Let's get started. The story begins, as many scientific tales do, with a bit of a misunderstanding. The name itself, rare earth elements, is a fantastic piece of historical branding that happens to be completely misleading. These elements aren't particularly rare. In fact, one of them, cerium, is more abundant in the Earth's crust than copper. You heard that right. The stuff in our plumbing and wiring is less common than an element most people have never even heard of. So why the name? For that, we have to travel back to the late 18th century, to a small village in Sweden called Ytterby. In 1787, a Swedish army lieutenant and amateur chemist named Carl Axel Arrhenius was exploring a quarry near the village when he stumbled upon an unusual black mineral. It was heavy, and unlike anything he had seen before, he named it Ytterbyte after the village. This strange rock found its way to a Finnish chemist named Johan Godolin. In 1794, Godolin analyzed the rock and discovered that it contained a new, unknown earth. Back in the 18th century, earth was the term for an oxide, a compound of an element with oxygen. And because this new earth was found in this one-of-a-kind mineral, they called it rare. Hence, the name was born, rare earth. What followed was over a century of pure chemical chaos. Scientists started finding these rare earths all over the place, but they ran into a massive problem. All 17 of the rare earth elements have incredibly similar chemical properties. They love to hang out together in the same ores, and separating them is an absolute nightmare. Imagine trying to sort a bag of 17 different types of sand, all of which look almost identical. For decades, chemists would announce the discovery of a new element, only for another scientist to prove that their discovery was actually a mixture of 2 or 3 or even more different rare earth elements that were stubbornly stuck together. It was a messy, confusing, and highly competitive period of science. The periodic table was a wild frontier, and the rare earth section was the most lawless part of it. It wasn't until the development of powerful new techniques like spectroscopy in the 19th and early 20th centuries that scientists could finally start to untangle this chemical knot. By shining light through samples of these elements, they could see that each one produced a unique spectrum, a unique fingerprint of light. This, along with X-ray spectroscopy, finally allowed them to properly identify and organize all 17 elements, from lanthanum, number 57 on the periodic table, all the way through to lutetium, number 71, plus 2 others, scandium and yttrium, which are honorary members due to their similar properties. And that little village of Ytterby? It now holds a unique place in scientific history, lending its name to not 1, but 4 different elements: yttrium, terbium, erbium, and ytterbium. No other place on Earth has that claim to fame. So we've established they aren't that rare, and they were a headache to identify. What then makes them so special? Why are these 17 elements the backbone of modern technology? The answer lies in their unique atomic structure, which gives them a set of superpowers that no other elements can quite match. You don't need a lot of them. You just mix a small amount into a more common metal, and suddenly, that metal can do extraordinary things. Let's break down their 3 main superpowers. First, and perhaps most importantly, is their incredible magnetism. Two rare earths, neodymium and dysprosium, are the key ingredients in the world's strongest permanent magnets. We're talking about magnets so powerful that they can be incredibly tiny and lightweight, yet still do a massive job. Think of them as the Hulk of the magnet world. These aren't your typical refrigerator magnets that can barely hold up a child's drawing. These are the powerhouses that make our modern world spin. They are in the tiny motors that make your phone vibrate, the tiny speakers that produce sound, and the read/write heads of hard disk drives. Without neodymium magnets, our electronics would be bigger, heavier, and far less efficient. Their second superpower is luminescence. This is the ability to emit light. Elements like europium, terbium, and yttrium are used as phosphors. When you excite them with energy, like an electron beam in an old TV tube or UV light in a fluorescent bulb, they glow with brilliant, pure colors. Europium gives us our vibrant reds. Terbium gives us our vivid greens. By mixing these, we can create the full spectrum of colors on our television screens, our laptops, and our smartphones. They are the reason modern displays are so bright and colorful, and they were also essential in the development of energy-efficient lighting, like compact fluorescent lamps and LEDs. Their third superpower is their catalytic prowess. A catalyst is a substance that speeds up a chemical reaction without being consumed by it. Think of it as a chemical matchmaker. Rare earths like cerium and lanthanum are brilliant at this. Their most common application is in the catalytic converter in your car's exhaust system. They help convert toxic pollutants like carbon monoxide and nitrogen oxides into much less harmful substances like carbon dioxide, nitrogen, and water. They are also vital in the petroleum refining process, where they help crack large hydrocarbon molecules into smaller, more useful ones, like gasoline. They make industrial processes faster, more efficient, and cleaner. So we have magnetism, luminescence, and catalysis. These three superpowers are the reason rare earth elements are woven into the very fabric of our technological society. And the applications are truly everywhere, often in places you'd least expect. Let's take a quick tour. We've already mentioned your smartphone. It's a treasure trove of rare earths. The neodymium magnets in the speakers and vibration motor. The lanthanum used to reduce distortion in the camera lens. The yttrium, europium, and terbium making the screen's colors pop. A single phone contains multiple rare earths. But that's just the start. Let's look at the green technology revolution, our global push to move away from fossil fuels. This transition is fundamentally dependent on rare earth elements. Take electric vehicles, or EVs. The high-efficiency electric motors that power them rely on powerful neodymium magnets. Each EV motor can contain about 1 kilogram of them. The batteries also contain a significant amount of rare earth compounds. As the world shifts to electric transportation, the demand for these elements is set to skyrocket. Then there are wind turbines. To generate electricity efficiently, especially the massive offshore turbines, you need a powerful generator. And those generators use enormous permanent magnets, packed with neodymium and dysprosium, to convert the motion of the blades into electricity. A single large wind turbine can contain hundreds of kilograms of rare earths. So the very technologies we are counting on to build a sustainable future are, for now, completely reliant on mining these specific elements. The applications extend into healthcare as well. Magnetic resonance imaging, or MRI machines, which give us detailed images of our organs and tissues, use massive superconducting magnets. But they also use a rare earth element, gadolinium, as a contrast agent. When injected into a patient, it helps to enhance the quality of the MRI images, making diagnoses more accurate. They are also used in X-ray machines and even in some cancer treatments. And then there's the defense sector. This is where the strategic importance of rare earths becomes crystal clear. They are indispensable for modern military hardware. They are used in precision-guided missiles and smart bombs, in the guidance and control systems, and in the fins that steer them. They're used in radar and sonar systems for detecting enemy ships and aircraft. They're used in lasers for targeting and communication. They're in the powerful jet engines of fighter planes. To give you a sense of scale, a single F-35 fighter jet, one of the most advanced military aircraft in the world, contains an estimated 417 kilograms, or 920 pounds, of rare earth materials. When you realize that these 17 elements are critical for everything from consumer electronics to green energy to national security, a very important question arises: who controls them? This is where our story takes a sharp turn into the world of geopolitics and global economics. The supply chain for rare earth elements is one of the most concentrated and politically sensitive in the world. For decades, one country has held almost all the cards: China. In 2023, China was responsible for mining over 69% of the world's rare earths, but the mining is only half the story. The more critical part is the processing, separating the individual rare earth elements from each other and refining them into the high-purity metals and alloys that technology companies need. And in this area, China's dominance is even more pronounced, accounting for nearly 90% of global processing capacity. This didn't happen by accident. In the 1980s and 90s, the rest of the world, including the United States, which was once a major producer, largely abandoned the rare earth market. The reason? It was difficult, expensive, and environmentally messy. China, on the other hand, saw a strategic opportunity and invested heavily, using lower labor costs and less stringent environmental regulations to become the world's dominant supplier. This has created a massive vulnerability for the rest of the world. A nation's ability to build smartphones, electric cars, wind turbines, and fighter jets is dependent on a stable supply from a single, strategic rival. This became alarmingly clear in 2010, when China temporarily cut off exports of rare earths to Japan during a diplomatic dispute. Prices shot through the roof, and panic spread through global industries. It was a wake-up call. Since then, countries like the United States, Australia, Canada, and others have been scrambling to reduce their reliance on China. There's a global push to discover and develop new mines and, crucially, to build domestic processing facilities. It's a new kind of gold rush, a strategic race to secure these vital materials. The global market is booming, projected to be worth over $8 billion by 2032, driven by the relentless demand from high-tech and green energy sectors. But as we rush to open new mines and diversify our supply, we're coming face to face with the reason we stopped mining them in the first place: the hidden costs. The extraction and processing of rare earth elements carries a devastating environmental and social price tag. This is the dark side of our shiny technology. The mining process itself, often done through massive open-pit mines, can lead to widespread habitat destruction and soil erosion. But the real problem begins when you try to separate the valuable elements from the ore they're found in. This process is chemically intensive. It involves using a cocktail of harsh acids and other chemicals to dissolve the rock and leach out the rare earths. What's left behind is a massive amount of toxic waste. For every single ton of rare earths produced, the process can generate up to 2,000 tons of toxic tailings, a kind of sludge filled with heavy metals like cadmium and lead, and even radioactive elements like thorium and uranium, which naturally occur alongside rare earths in the ore. This toxic and sometimes radioactive waste has to go somewhere. In some regions, it has been stored in poorly contained tailings ponds, leading to catastrophic environmental consequences. There are well-documented cases, particularly in China and other parts of the world, where this waste has leaked into the groundwater, contaminating drinking water for entire communities and rendering agricultural land unusable. Rivers have turned yellow with pollution, and local populations have suffered from a range of health problems. Beyond the environmental damage, there are the social impacts. Workers in these mines are often exposed to hazardous materials with inadequate protection. And the boom and bust cycle of mining can lead to social disruption and poverty in the communities that host these operations. It's a profound and uncomfortable paradox. The elements that are supposed to be paving the way for a green future are often extracted using some of the dirtiest and most destructive methods on the planet. The vibrant colors on our screens are enabled by a process that can leave the land and water in other parts of the world gray and lifeless. It's a stark reminder that in our interconnected world, there's no such thing as a clean break. The costs of our consumption are always paid somewhere, by someone. It's a grim picture, but it's not the end of the story. The growing awareness of these challenges is driving a powerful wave of innovation aimed at creating a more sustainable future for rare earth elements. The path forward is threefold: recycling, finding alternatives, and building a more responsible supply chain. First, let's talk about recycling. Right now, it's estimated that less than 1% of rare earths from products at the end of their life are recycled. That's a shockingly low number. The reason it's so difficult is because these elements are used in such tiny quantities, and they're mixed into complex products. Getting the few grams of neodymium out of an old hard drive or the traces of europium from a broken TV screen is a huge technical challenge. But it's a challenge that scientists and engineers are tackling head-on. They are developing new methods, from pyrometallurgy, which uses high temperatures to melt down and separate materials, to hydrometallurgy, which uses liquids to selectively dissolve and recover the elements. Companies are also exploring ways to design products that are easier to dismantle, making the recovery of these valuable materials more feasible. This idea is sometimes called urban mining. Instead of digging new holes in the ground, we can mine the vast landfill of our discarded electronics. The second path is the search for alternatives. The best way to reduce our reliance on a problematic material is to find something else that can do the same job. Researchers around the world are in a race to develop new materials that can replace rare earths, especially in their most important application, magnets. They're exploring things like iron nitride magnets, which don't use any rare earths at all. While no single material has yet been found that can match the all-around performance of a neodymium magnet, especially its ability to work well at high temperatures, progress is being made. A breakthrough in this area could fundamentally change the game, reducing both the geopolitical tension and the environmental footprint of technologies like EVs and wind turbines. Finally, there's the push for a more diversified and responsible supply chain. This isn't just about opening new mines outside of China. It's about ensuring that wherever these elements are mined and processed, it's done to the highest environmental and social standards. This requires collaboration between governments, who can set strong regulations, industries, who can adopt more sustainable practices, and consumers, who can demand greater transparency. We need a system where we can trace these materials from the mine to the final product, ensuring they weren't produced at the expense of a community's health or a region's ecosystem. So where does that leave us? The 17 rare earth elements are a perfect symbol of the double-edged sword of technology. They are the invisible force that enables so much of our modern world. From the way we communicate and entertain ourselves, to the technologies that hold the promise of a cleaner, greener future. Yet, their journey from the earth to our hands is fraught with complex challenges, geopolitical rivalries, environmental devastation, and social costs that we are only now beginning to fully understand and address. As our world becomes more technologically advanced, our reliance on these hidden ingredients will only grow, and with that growth comes a greater responsibility. The future of our technology, and in many ways, the health of our planet, may well depend on our ability to navigate this complex landscape. It depends on our commitment to innovation, not just in making our gadgets faster and smaller, but in making their entire life cycle cleaner and more just. The next time you pick up your smartphone or see a wind turbine spinning gracefully on the horizon, take a moment to think about them. Remember the 17 hidden elements that make it all possible, and the complex, challenging, and crucial journey they took from a mine to your hand. Thanks for tuning in to G Fun Facts Online. Join us next time for another deep dive into the science that shapes our world.